Okay, so hi guys, I'm Samyak Pratyush Prasad, and today's talk is on the thermodynamics of indefinite causal orders with the quantum switch. So we'll be breaking this up a lot. We'll be talking about what is quantum, what is indefinite causal order, what part of thermodynamics I need, all of that. So this project actually I did with Dr. Manabendranath Bera at IC Mohali and Dr. Alexia Offevs and Dr. Sid Brancier at NEL. So, okay, let's just get right into it. Yeah, so as you would have seen my contents, I'll be starting with the very basics of quantum theory. I will use only qubits for this. Satvik has already given a very rich mathematical structure that is used in quantum theory. What I'll do is I will look at only qubits and we'll actually try to see how to physically interpret the vector spaces that the Hilbert space, basically what Satvik explained last time. So that's what I'll do here, and we'll be talking about starting from very basics, pure and mixed states to water channels and cross operators. Second part, I'll go a bit quick. It'll be on the basics of thermodynamics. I'm sure most of you already know it. Some part of it will be from statistical mechanics, so it will be kind of a revision this part. And I'll show you how these ideas translate to the quantum regime without really giving a very good proof, but we'll be just using the classical results and switching over to quantum. So, or else it'll be too long, this part. So yeah, that's what I'll do here. And the third part is about a part of my project that I did for my master's, which is on indefinite causal orders. And we'll see some interesting questions here. I'll come up. Okay, so let's just start with the basics, what qubits are. Okay, so qubits are, as you all know, two-level quantum systems. We denote it by 0 ket as a state and 1 ket as a state. So from last time, if you see, these were the basis elements of the Hilbert space. What I want you to think in this talk is like this. A two-level quantum system has a ground state, which will be given by the 0 ket. And it will have an excited state with a higher energy gap. The energy gap between the ground state and the excited state will be delta, and the excited state will be given by 1. Okay, so these kets, 0 and 1, just label the state that you are in. Okay, so this will define our qubit system. Okay, now from last time we saw that qubits are, or any quantum state are expressed as density matrices in the matrix space that Satvik talked about. So I just wrote a two-dimensional qubit here with P being the occupation probability of the zero element, of the zero state, basically. So what I want you to realize is that these diagonal elements actually give you the probability of occupation. And the off-diagonal elements, these C and C star, give you some information about the coherence or the superposition present. These are known as the coherence terms. And in literature, you'll see these referred to as populations and things like that. So these are just terms I'm throwing at you so that, even if when you read literature, you'll understand what they are. So yeah, so this is that. So one thing here, I mean, when these are 0, then you know for sure that in this basis, you do not have superposition when C is equal to 0. So that's that. Now, as I told you, we'll be thinking of qubits as systems with the energy spacing. So for this, I define an energy operator, or the Hamiltonian of the qubit, which will be given by delta 1, 1. So because the energy spacing is delta, I can arbitrarily take my ground state to be at 0 energy. I define it as 0 energy. And the excited state will hence be at energy delta. Okay, so this is given by the Hamiltonian delta 1, 1. Okay, and the average energy of any qubit will be just given by this trace formula, rho times h, and you take the trace of that. Will be the average energy of the qubit, whichever qubit you have, any rho. Okay, so let's go to the concept of pure and mixed states. So this too is pretty simple to understand. Pure states are just linear combination of basis elements. So it really depends on which basis you are in. And actually, yeah, so psi can be written as some alpha 0 plus beta 1, or some, if you go into some other basis, you can write like alpha prime plus beta prime minus, something like that, where these coefficient squares are always equal to 1 because the coefficients give you the probability of being in a particular state. Okay. So now to think about mixed states. So this is how I think about it. So imagine you have a state preparator or some device which prepares the 0 state and another device which prepares the 1 state. Now imagine that these devices work at random times. So with probability 1/3, it creates the 0 state, and the second device creates the 1 state with probability 2/3. So at random times, this box will get filled up with the state 0 and 1, right? And the probability of this box having the 0 state will be 1/3, and this box having the 1 state will be 2/3. But how do you write that as a state? So you can't write it as a linear combination of the basis elements like this. So this is why actually you need matrices to describe this classical ignorance that we have because of these probabilities. So you write a matrix where the 1/3 is the population of the 0, 0 state being occupied, and 2/3 is the probability of the 1 state being occupied. So as I said before, these actually give you the occupation probabilities, right? So this is a mixed state. This is what is known as the mixed state, and it can't be written as a pure state. Okay, so that's all I need you to understand. Mixed states are just statistical ensembles of pure states. You can say that. So now we come to a very nice interpretation of pure states and mixed states. So let's see. So qubits can be, I've shown here, this is the block sphere, known as the block sphere, and the qubits, any qubit can be expressed as some point inside or on this block sphere. Okay, why is that? Well, a little bit of math. So any row can be written as half times the identity element. Identity is just, 1, 1 on the diagonals. And some r, this is known as the block vector of the state, and sigma. Sigma are the Pauli matrices. So I hope you know the Pauli matrices. If you don't, it's okay. I mean, you can ask, but yeah. So basically these states can be expressed here. And what it actually means is this radius r gives you this r. Okay. And these elements give you the Rx, Ry, Rz, these elements on the R. So, and that is these Rx, Ry, Rz are given by the trace formula with the Pauli matrices. So it's as simple as that. So you can actually, any state, any point you take, you'll have some Rx, Ry, Rz, which you can just substitute here and you'll get a quantum state, qubit state. Okay, in general, actually, there are ways, this is just for information, there are ways of representing, there's a block sphere representation for higher dimensions also. So that is just for information, where you'll no longer be dealing with Pauli matrices, but a larger set of matrices here, and Rx, Ry, Rz, and one more dimension. So that's there. And what is important to note, why this is useful to us is because the surface of the block sphere gives you all the pure states. So R equal to 1 represents the pure states, and the center element, this element, there's a single mixed state that is given by identity by 2, which is given by R equal to 0. So you see the completely mixed state actually just has half on the diagonals. That means the occupation probability of 0 and 1 is just half. That means you don't really know anything about the system. You do not know if it's a little bit more 1 or a little bit more 0. So what we say is that you do not have any information about the completely mixed state. Okay, so that's how we think about it. And as you can see, the pure state, you know everything about it essentially, because you have the state and you can evolve it, you know exactly what is going to happen. Okay, there's no probabilistic mixture happening on the pure state. So that's what we mean. So this R kind of gives you the amount of information in a sense. But let me make that more concrete. But before that, I'll talk about evolution. Okay, evolution on the block sphere. This will be required to know how information also changes. So information is something that we'll be dealing with in this talk. So that's why I'll be talking about a bit about that. So yeah.
Hi, so I had a question before that.
Yeah.
So is there any particular reason why the density matrix, which represents
Mhm.
the this mixture of pure states,
Mhm.
so is there any particular reason why it is represented by this 2 cross 2 matrix? Like, why does it have to be a linear combination of outer products?
Oh, so it's basically, you see, you can't write it as a state vector, one,
Right.
right? So what this tells you is that there is some classical ignorance that you have regarding the states. Now, why it's the outer product? One way you can think about it is it works. Okay.
Okay. Yeah.
The second way of thinking about it is actually there are these theorems which tell you that these kind of operators will definitely give you the statistics that you get from quantum experiments. Okay. And
Okay.
these
Okay.
operators can be represented by matrices.
Okay. So this kind of a structure fits in with the theory.
Yes, basically.
Okay.
Okay, so there's a lot of things related to it actually, but yeah, you'll find that in
Hey,
math.
can I add something?
Yeah, sure.
So Kunal, your question was that why are we writing this as as it is written? So one answer can be that what we deal with in quantum mechanics is the probabilities, and here somehow we are applying the basic rules of probability, like product rules. So one is your statistical probability, which is coming from your classical ignorance, and one is coming from quantum probability, which is Bond rule. Now,
I've not gone there yet, so
okay.
that's why I didn't want to talk about it.
Oh, okay, okay. But I
Yeah.
think that can be, more
Okay, okay. I'll let you complete. Sorry. Okay.
Okay. Okay.
Go ahead.
okay, yeah, that's it. Like, so here, like 1/3 is the factor which is classical factor, and then probability coming from 0. So you have like from first beam, you pick with 1/3 probability, and then what is a probability of psi, which is inner product with 0. So you can write the probability. So it is kind of that.
Yeah, basically, what I think he's trying to say is that when you have these coherence terms, these can affect these probabilities also, because when you see the evolution, it will kind of mix these coherence terms with the classical ignorance terms. So that can really change the probabilities of being in some state. Did I get it? Right. I mean, yeah, I think
Yeah. Okay. Thanks.
that I hope it makes sense, right? Yeah. So yeah, density matrices are represented by matrices. Then yeah, evolution. Okay, so evolution. Usually, when we talk about quantum evolution, the most famous thing that we talk about is the Schrodinger's equation. So this Schrodinger's equation actually talks about evolution of isolated systems, and that's very important because it tells you that you know everything about the system. You do not have any external information coming in, and the complete evolution of this system is described by the Schrodinger's equation. Every time you have some external interference, the Schrodinger's equation will not really be satisfied unless you take into account the external information coming in. Now we'll go into more detail, but just keep that in mind. The evolution of isolated systems that is given by this equation is represented by unitary evolution, basically. So this unitary evolution basically comes from the Schrodinger's equation. Okay. Now the unitary evolution is special because, as you can see, this U is a matrix, U dagger and U dagger U. This dagger represents complex conjugate and with transpose. Okay, so what you do is, so U dagger U is equal to the identity element. Okay. What this means is that, this I think we saw last time also in Sathik's talk, but what this means is that when you evolve a state from psi to U psi, what will happen is its norm will not change. It will remain one. So what this really tells you is that you can rotate the state on the surface or wherever. You can just rotate the state using a unitary evolution, but you can never decrease the radius. Right? Unitary evolutions are just rotations on the Bloch sphere because they preserve the norm and hence they can't reduce the radius. It's not possible. Okay. So that's something that's important. Now we'll talk about this term that I'm just throwing around, information. So that kind of comes from entropy that we talk about. So entropy for qubits is given by this formula known as the von Neumann entropy, where you take the negative trace of rho, the ln of rho. Okay, if you have any problems with such formula, you can ask me, I'll tell you. But this is the formula for von Neumann entropy. And if you see, when you write rho in a diagonal basis, the diagonal elements will be the pi's here. So this is the formula for Shannon entropy. This, in a sense, tells you how much information you do not have about the system, but the amount of information that you can get when you measure the system. Okay, so it is the amount, again, I'll tell you, the amount of information that you do not have right now without measuring the system, but you can get it after you measure the system. So this is the average amount of information, in a sense. So this is the way I think about it. This is the intuition that I'm trying to provide. So let's see why. Okay, so first of all, let me tell you, the entropy for all pure states, all surfaces, all the states on the surface of the block sphere is 0. This can be easily calculated. I'll read this as an exercise also. And for any state below or inside the block sphere, with the radius not equal to 1 and less than 1, basically, entropy is always greater than 0. That means for mixed states, you have the ability of getting more information after measuring. So that kind of tells you, okay, there is some classical ignorance if entropy is greater than 0, right? Yeah, and entropy is maximum for this state, for the completely mixed state, and it's the entropy of the completely mixed state is really 1 bit or ln2, right? So that you can calculate also. I mean, it's pretty simple. Because 1 bit, because you have a single qubit which is described on this block sphere. Okay, so this is what I'm trying to tell you. S of rho, or the von Neumann entropy, or just entropy, is the measure of information content
Samyak,
in the state room. Yeah.
someone has asked in the chat that in time evolution, the norm does not change. Question.
Yeah. Yes.
Yeah,
unless the time and evolution is, yeah, the answer is also given. So yeah, unless you have some external agents coming in which you don't look at. So we'll get into that. Let's see. Okay. So regular time evolution given by the Hamiltonian does not change the norm. So basically, every time, so every state that is evolving with time will just move on the block sphere, and that's all. We just rotate on the surface. If it's a pure state, or if it's inside, then it'll just rotate in circles in whichever direction. Okay. Yeah. One fun fact about this is that every time you rotate, obviously you don't reduce the radius. So any rotation is basically the unitary operation. So any unitary operation does not even change the entropy. So this I say because I want to tell you that unitary evolution cannot add any information or remove any information from the system, right? Because they're just rotations and you can't really do anything with it. You can add or remove information from it. Okay, so the entropy, because of unitary evolution, does not change. And this also tells you something interesting. Unitary matrices are actually used to change the basis if you speak about it mathematically. So you see that if you apply a unitary on rho, on this matrix rho, you'll get a state in a different basis in a sense, but this entropy will remain the same. So one important point here is that the entropy is basis independent. So entropy does not depend on the basis that you're choosing. Obviously, because the basis should not tell you how much information content is there in the system. Basis is just a representation of your system, a way of telling you, the probabilities inside the system and the amplitudes. But it really doesn't tell you how much information is there. That is given by the entropy, right? And interesting point again, this entropy can be written as a function of this mod r. That's the radius that you have here. So it completely makes sense when the entropy is 0 on the surface and it becomes maximum at the center. So that's it. So we have talked about entropy. Now, what I want to talk to you about is entanglement. And using this, I will go into the fact that if we have just unitary evolutions given by Schrodinger equation, how can we really talk about anything else? Any other transformation that we have in quantum mechanics, everything cannot be unitary. You have some mixedness. So how is that evolution defined? If I tell you that, okay, Schrodinger equation tells you everything about the evolution, right? So to do that, first I'll go into entanglement that Satvik actually talked about. But I'll give you a way of actually creating entanglement and a particular setup which makes it easy to understand what entanglement is and how information is related to this. Okay, so there is a gate. So gates are nothing but just input-output devices. Okay, that's simple to understand. This is known as the control NOT gate. Okay, so this whole thing is the control NOT gate, and this whole thing together is a unitary operation. Because every time you have everything that you want that evolves together, it is described by the unitary. There are no external systems involved here. There are just two systems. And this control NOT gate is a 2-qubit gate, right? As you can see, so this is 1 qubit, this is another qubit. So what this does, okay? So when you have, we'll call this the system and this an ancilla. So this is another terminology that you'll see in papers. So when this is 0, this will remain 0. But when this is 0, this will change depending on the state of your system. The ancilla will change depending on the state of your system. When this is 0, it will not change the system. But when the system stated 1, then it will flip the bit. Okay, it'll just make it 1. Way to write that is, so the final state, combined state of the two systems will be represented as 0, 0, or the tensor product of the two Hilbert spaces. Okay, and here 1, 1. So you see, this flips the bit, this gate flips the bit depending on the system state, right? So that's why this flipping of the bit is controlled by the system that you want to talk about. Okay, so now, so this is what it does. Now I will, this is something I already told. So this is another point that I want to make. Yes. So what you can see is that because the final state of the second qubit is dependent on the first qubit, it in a sense correlates the two systems, right? So that is important because if this was 0, this will also become 0. If this is 1, this will also become 1. So it's correlated in a sense, right? So that's that. Now, imagine you start with the plus state. Plus state is just equal mixture of amplitudes of the 0 and 1 state. So you can see this. And so this is the plus state. And when you start with such a superposition state, what you get is this state, this phi, given by 0, 0 plus 1, 1 by root 2. Now, if you can see, if you remember from last talk, this is an entangled state. This cannot be written as some alpha. This cannot be written as some, alpha ket tensor beta. You can't write it like this. This is not possible, right? So that's why this is entangled. I hope you remember this. If you have any doubts from this, you can ask. So
going from this initial state to final state using this sort of a gate, is this still a unitary transformation?
This is still a unitary because you see, this whole unitary defined by, acts on the two systems together. Okay. And any evolution which takes into account every system has to be unitary because we believe in the Schrodinger's equation.
Okay.
So in a sense, you can think that, or else you can, if you write down the gate, the operation of this gate, and you do UU dagger, you will get identity.
Yeah, right.
Okay, so that also works. I mean, whichever interpretation you like. So what I've shown you is a prescription of how you can create entangled states, right? So this is just use a control NOT gate and use superposition, use the 0 state here, you'll get this. Okay. Yeah, now I want to tell you about something very interesting here. Now imagine I make the state. So this is the combined state of the two systems. But now imagine I do not look at this state. For example, say after I do this operation, something happens in my lab and I lose this bit. Okay. Now what happens is I only have access to the system state, the final system state. The thing is, when I can't look at the second state, because these states have become entangled now, I have no information about my system state. This tells you, because this becomes the diagonal completely mixed state, if you can see. So this operation that I've shown here is a trace operation. That means you basically, what you do is you remove that system, or you do not look at the system basically, and you only have access to the degrees of freedom of your system finally. So that's it. And this will give you the completely mixed state. So what does that mean?
Yes, you meant ancilla, right? You ignore ancilla and...
I ignored the ancilla, yeah. What did I say? Did I say something else?
Maybe system both the times.
Oh, sorry. I ignore the ancilla and I just have the system. Okay. Yeah. So this gives you the completely mixed state. So this tells you something really interesting. That is that this correlation that I've created by creating this entanglement has some information. Because using a unitary, by just not looking at a system, I have gone from a pure state to a completely mixed state. I've completely reduced the radius. I've maximized the entropy here of the system, right? So the correlations here, the entanglement between the states, have some information which is lost when one of them is not taken into account. Okay. So this is something that we use to define how measurements takes place and how we define channels and things like that. So everything clear till here? I mean, does this make sense? Because that we have lost information because we have actually lost a system completely. And these were already correlated, so we have actually lost all the information on the system also. Okay, I'll proceed then, if this is clear. Now let's talk about quantum measurements. Okay, so say in the normal way in class that you learn is that you have some observable. Now we saw in the last talk that any observable can be spectrally decomposed like this. And what is important is that I will decompose my state into a linear combination of basis elements which actually depend on my observable that is being measured. For example, if I'm measuring the spins, I'll just decompose my state, the quantum state, into either say up or down or things like that. Or if I'm measuring polarization, then horizontally polarized and vertically polarized. It depends on what you want to measure in, which basis you want to measure, basically. So using this, what we see is that if you want to measure this lambda 0 of the observable, you get that with probability alpha square of this side, so alpha square. And you basically, what you do is you project the system onto the 0 state. So this is how it's usually taught in class also. And with beta square probability, you get the 1 state by projecting the state onto the 1 element. Okay, and that's all. So there is, so this is said, and there is instantaneous collapse of the system. Now the average energy of the observable is given by repeated measurements, and it's given by this. So you do this measurement multiple times. What you get is some 0 with probability alpha square, 1 with probability beta square, and on average, this is the value that you get of the observable that you're measuring. Okay, so yeah, so that's how quantum measurements are actually thought about or taught in class. But what we have ignored here is the fact that we don't really look at the system directly. For example, I don't look at an electron directly or a photon directly. I always need some device that couples to this photon or electron or whatever and measures the state, right? Here, the measurement device is not taken into account. Okay, so we need a theory where there's a measurement device which couples to the system, extracts some information from the system, and measuring that measurement device, actually looking at the measurement device, actually tells you, gives you some information about the state. So let's do that. Okay, so here I call this second, the ancilla that I was calling before, I call it the quantum meter. Okay, this will be a device or a quantum state which will measure my system. Okay, my system is in Hilbert space Hs, and the observable may be some S, and this is the eigenbasis. But we are just talking about qubits, so you can just think of spins or spin up and spin down or things like that. And but the important part is my ancilla or the quantum meter is also quantum now, as in it can be described by states on the Hilbert space. Okay, what I do is I have a spin up state, I couple it with the ready state of the answer. So this A0 will be some arbitrary state, which I call the ready state of the quantum meter, and I couple it like this. So this whole thing is actually, I've not drawn it correctly. It's just a whole unitary interaction here. Okay, and after the unitary interaction, what happens is, just like the way we saw with the C0 gate or the control NOT gate, when this is up, this will become some A up. So these are correlated now. Whenever this is up, this becomes A up. Whenever this is down, let me just draw that also. Whenever this is down, comma, this becomes A down. Okay, so these are correlated like this. Okay, so now I'll tell you some terms that are used. There's something known as pre-measurement, and that is related to this coupling. So say I decompose my initial state in the basis of the observable and have A0. I put this interaction term, U int, and it will correlate every single quantum meter state with the system state. So every S has an AS. Okay, so every up and down will have an A up and A down. This is the same thing that we saw with the control NOT gate, very similar. But this up and down need not be the same, A up and A down need not be the same states or in the same observable basis for the quantum meter. It could be any other basis. Okay, it need not be just 0, 0 or 1, 1. It could be anything. You just have to make a correlation. Okay. Now, there is something known as post-measurement. Post-measurement is something that we did previously, where we said that, okay, in any quantum measurement, I project the system onto just 0, 0 or 1, 1, right, with some probability. So that will happen from using the post-measurement. So now what I do is I project the ancilla or the quantum meter onto one basis element or AK or something like that. This occurs with probability alpha k, or this amplitude squared basically. And that will give you that this system is in state K whenever the quantum meter is observed in state AK. That means for the spin example that we saw, if I project the quantum meter in the A up, I'll get finally the system also in A up. So just looking at the quantum meter, I can tell you what the state of the system is. Okay, so this is how we model a measurement device, coupling with the system and actually measuring the system. Because really this is what happens in actual experiments. We never directly go and look at an electron, obviously. So yeah, this is what happens. Now I will step it up a bit here by talking about generalized measurements.
So in the last example, we were measuring the state of AK, and using that we were using that to extract what the state of the first system was.
Mm-hmm.
Was it something like that?
Yeah. So I look at only AK. Okay. I look at it. I look at my measurement device. The state of the measurement device collapses to AK. Okay.
Right.
And hence this K tells me that, oh, my system is in state K.
Okay. Yes.
So if A up, then I know, oh, my system is state up, because I really can't look at the spin of an electron. I look at some device. Or for example, think about
So we correlate something with the spin of the electron and use that, measure that thing to find what the spin of the electron is.
Yeah. Think about speedometer, right? You don't directly measure the speed of a moving car. But when you look at the speedometer, you see that, oh, my pointer is at, say, 80 kilometers per hour. So I know my car is moving at 80
Right. Yeah.
So it's exactly like that. Yeah. But here, the important point is we have correlated the system and the ancilla, but both are quantum mechanical. So there can be superpositions like this. So this collapse is actually given by the amplitude squared, the probability of collapse. Okay. So
Samyak?
Yeah.
Am I audible? I hope I'm audible.
Yeah, you are.
Yeah. So there is an extra assumption here, right? These states of the ancilla A corresponding to the states of the system, they are orthogonal, right? Because otherwise, even if you measure AK, then there might be overlap with something. Yeah.
So the thing is, whenever you're making this, see what I've done here is I've made a direct correlation. Okay, I'm not saying that AS, for example, AK can also give you information about K minus 1. For example, let me just tell you this. So what you're saying is right, but I'll tell you why exactly. So I've said that AK corresponds to K state, right? But it does not correspond to K minus 1, for example. Or it does not correspond to K plus 1. Okay. So there is no spread here between the states. So when I look at AK, I know it is exactly, the system state is exactly K.
What do you mean that it does not correspond? I mean, it's.
So I have correlated the states, right?
I
have correlated it exactly. There is no.
Yeah, so basically that does not correspond. It's like you're saying that these are distinguishable in the sense that they are orthogonal. So it's just another way to say that, right?
Yeah, no.
Because if they're not, then you can.
The point I'm coming to is that if the system states themselves are orthogonal. Right. So they are orthogonal because I've chosen the to be in some basis. I say that, okay, I have a one-to-one correspondence with another basis, AS.
Yeah.
Okay. Now you're right. So there are cases where, you have this spread and these basis elements are not really orthogonal. So yeah. So that's not really an assumption, I would say, but that's just the way we have done it. Right. Because that's what we want.
Yeah.
Okay. So
you mean that guaranteeing that the eigenbasis is orthogonal, the states in the eigenbasis are orthogonal to each other, the corresponding correlated basis is also orthogonal.
Yeah, that's what we want. That's what we want this interaction unitary to do.
All right, we have prepared it in such a way.
We have prepared it in such a way, yes.
That would be like an ideal scenario in a lab, but that might not be the case.
Yes.
That's why you get, let's say, errors or something like that.
Yes. So one way to think about it classically, what Satvik is trying to say is that, for example, in the same speedometer example, the needle is not really very sharp. It has some spread to it, some width to it. So when I measure 80 kilometers per hour, it could actually be 80.5 kilometers per hour or 79.5 kilometers per hour, anything in between that, right? Because there's that spread. Okay, but there is much more to it, and there is no time to go into it because it's a theory called peak measurements. So that's the thing. So yeah, I'm just talking about one-to-one correlations. Okay. So yeah, any other doubts here?
So my question is that you pointed that we can't measure spin directly. So my first question is, why can't we measure spin? And another is that which depends on that the system, ancilla system you are using. Is it always necessary that it should be macroscopic, or it can be microscopic and you can get collapse?
So I would say, answering your second question first, if you can look at it and measure it, then that's what you use. For example, by just looking at polarizations of photons, you can measure spins. Okay, by interacting the photon with the spin degree of freedom. there are experiments that do that. Okay.
Yeah, so that's why my question is that what we can look at and what we can't look at. How?
So the thing is, to measure the polarization, what you have to, have some apparatus also interacting. So there's a whole thing to it. But the thing is, what I'll show you in the talk also, this coupling that you have with the meter actually has an energetic cost. And that's what is important. You're actually getting some information from this coupling also, or losing some information from this coupling. So that's what is actually important. Okay. And answering your first question, I mean, you can just think about a Stern-Galak apparatus where you have, the state up or down, some size state. And this Stern-Galak actually just shoots beams of argon, silver, I think, I forgot. And then you get some state up and state down. This represents the up state. This represents the down state, right? But what we have ignored here is this magnetic field that is there, right? So this I can model in this way exactly. Okay, and this whole apparatus kind of becomes my quantum ancilla, in a sense, because it's going up.
I think it's a wave function of particle. So external special mode is your ancilla, and internal is your system. But anyway, so the whole point was that we always measure in some kind of position basis or momentum basis. Here is also.
So that's what I started with, right? Because your observable defines your basis that you're measuring in. But
what we always require for ancilla, it's empirical evidence that it's always position basis or momentum basis. In fact, position basis preferably. But it's not clear in assumptions. So that's why I was just pointing out.
Wait, are you saying that you need to know the position of a particle to measure to perform any measurement?
You just explore all the examples which have been.
Okay, I'll check, but I don't think it's true. But okay, I'll check it out. I mean,
we can discuss.
Because there are ways of measuring polarization without measuring the position of the photon.
You check it.
Okay, I'll.
Your final information which comes is coming from the position basis.
Okay. Maybe. Fine. Then we'll proceed. Then we don't really need to complicate it that much. We just need this actually.
Yeah, sure.
Okay. So anything else, or I hope this discussion did confuse all of you. That's a problem. Okay. So I hope we have understood this correlation that we have. Okay. Now I'll move on to something known as generalized measurements. So what I did here in the previous example is I projected my quantum meter into a state of the correlation basis. For example, if this is up, I correlated with A up, and then I project my ancilla in this A up or A down basis, right? I project in that way here. But now, what if something goes wrong, say, and I do not project it in the A up or A down? So what happens is my quantum meter state finally changes to some Mi, okay, where Mi is the basis of projection, say, and my state itself changes to some other rho I. Okay, so if the measurement of the quantum meter is not done in the basis of coupling, that was A up and A down, the measurement back action. So this is the measurement back action that happens. So we measure this and there's a back action on the system. Will not be projective on the observable basis. Okay. So you can have a degree of mixedness here, you see. Yeah. So for example, what I mean is if it is not projected on A up, this will not be up or down. This will be something else entirely given by a density matrix, rho I. So each rho I depends on the state here, Mi. Okay. So that rho I is given by some formula like this. So last time, I think Sathik talked about positive operators and things like that. And POVMs, positive operator value measures. So this EI, the elements, are elements of the positive operator valued measures. related to each outcome I occurring with probability pi. So you see this trace formula gives you the probability pi that rho I has been measured in a sense, because I collapsed in a wrong basis or something in a basis mi. Okay, and this is the final state that I'll get. Okay, and these ki are just given by this. So as you can see, this tells you nothing but you interact between the system and the quantum meter, and then you project it onto the mi state of the quantum meter. That's all. That's all this is. So this is ki acting on psi. Okay. So these EI are known as these positive operator valued measures, or elements of positive operator valued measures, because this in a sense gives you a way to measure the probability. Okay, when you write this trace formula, you need to have this EI elements, which will tell you, okay, this ith outcome is related to the probability pi. So that happens because you have this positive operator valued measure. Okay, so it is actually a measure. It's an operator valued measure, which gives you the probability in a sense. So that's why we have these terms. You'll see these terms in a lot of literature. So.
This rho I is the collapse state here, right?
Yeah, of the system.
Okay, okay.
Yeah, when you are only looking at the system. Okay, yeah, these POVM elements sum up to identity and in a sense describe the most general kind of measurement possible on the system using the meter. Okay, so if I can actually do the opposite, if I can write EI as some POVM and I can have a set of them, then I can actually tell you, okay, using this, I can have a set of measurements on my state, which are generalized measurements in a sense, which don't give you really projections on observable basis, but something else. Okay, so these are rho I. So I told you this because now you see, using this prescription, I can really change the state or the radius actually, the Bloch sphere radius of my system, right? Using this. By just not looking at this, I can really, if I have some state R, some initial radius R, I can make it R prime. So let's see how that is done. Okay, so we had the Bloch sphere and unitaries were just rotations on it, right? So how do we evolve a system and reduce the radius of the Bloch sphere on the Bloch sphere if the unitary operations can't do that? So this leads to the idea of channels, which are non-unitary basically. Unitary channels are basically unitary operations. Okay. So what I want you to understand is this reduction in radius, as we saw, was some loss in information. And this loss in information also came from disregarding correlations with another system, right? So I want you to look at this figure now. We have a system here. I've changed the notation a bit. We have a system here, and now I call this the environment, okay? Not the quantum meter, not the ancilla, but an environment. Okay, this environment can have a lot of degrees of freedom. I just take a basis element from there and call it E0. Okay, I have a complete unitary acting between the system and environment. Okay, but the thing is, with the environment, I can't really look at the environment at all. There is no way of looking at the environment. Environment is defined to be in a state which cannot be accessed. Okay, so what I do is I trace over that system. I do this coupling. This coupling happens in a particular way, and I trace over it. Okay, what I get is some action of phi of map phi on rho, or rho 0 actually. There should be a 0 there. Sorry. So action of phi on the initial state. Okay. Yeah. So this action of phi is given by tracing over the environment E when this interaction has happened between the system and environment. So this is rho 0 is the state of the system, tensor the state of the environment. Here the assumption is that my system and environment are not initially correlated. So they can be written as a simple tensor product. Okay. So what this gives you is finally, when you solve it, it'll give you the same the KIs that we saw last time. Okay, and this can be actually written as Pi times rho I. Okay, so an easy way of thinking about it is, you remember the initial example I gave you of two state preparators or preparation devices going into a box with 1 and 0 and them being related with some probabilities. So it is like that. The states have gone into a box with a lot of row i's, row 0, row 1. Let's just draw it. So I have a box with row 0, row 1, row 2, etc. coming from with some probability P0, P1, and P2, right? And the average state of this box is given by this Pi times rho I. And what we saw from last time, one sec. What we saw from last time is this Pi times rho I are just these elements, Ki, rho naught, Ki, summation over all i's, right? That'll give you the average. So these Ki elements or these operators are known as Krauss operators that describes the channel action on the state. So you see, this just having these Ki can tell you how my state evolves to some other state without really needing this whole ancilla picture or the environment picture. If I can just tell you, give you some Ki, I can make some Ki and give you, prescribe it to you without talking about any environment, I can still define a channel like this. And this channel is obviously, it's trace preserving. This is also another quantum state. All of that is satisfied. Okay. Okay. Any doubts here? Yeah. So we are done with what are channels essentially. So they're basically maps from one state to another. And this can actually lead to, any arbitrary rotation plus reduction in radius or increase in radius. Any doubts here? I hope
Hi, Samyak.
Yeah.
Yeah, I just wanted to, make a couple of connections with what we talked about last time.
Yeah.
So if you can go to the slide where you first define the block ball before the entropy, I think, when you define the entropy. So I just have two things, less mathematical subtleties as I wanted to point out.
This one?
Yeah. So I just need this picture. Yeah. So if you remember last time we talked about positive semi-definite operators, right? So I just wanted to make a connection with the geometry. So if you just look at positive semi-definite operators which are not normalized, then you get what is called, in geometrically speaking, you get a cone in three-dimensional space that extends infinitely, right? Precisely because there is no normalization, so it can extend infinitely. And so here, everything is normalized. A quantum state is a positive semi-definite operator which has trace equal to 1. So when you impose the trace normalization, it's like you have a convex cone and you're cutting it with a plane so that the intercept that you get is like a circle, which is a bounded object, and it is no longer a cone. It's still convex in the sense that you can, take any 2 points and then join them via a line, and then the line will still lie within the body. That's what the meaning of convex is. Yeah. So originally you had a cone, which was just the set of all positive semi-definite operators. And then once you impose the normalization, you kind of cut it with the plane, and then the circle, the intercept that you get is like the geometry of the actual set of quantum states, which are normalized positive semi-definite operators. And representation of it is given by the block ball. It's like higher dimensional version of this. Instead of a disk, you're getting a ball. It's still a convex body, but it does not extend indefinitely, right? So that's just one point. And the other point is in this definition of entropy. So if you look at the expression inside the trace, you're actually taking log of an operator. And that's mathematically, that's a question in itself. If you have a matrix, how do you define the log of the matrix? You can think of many ways to do that, right? You can write down the entries of the matrix in a D cross D array, and then you can think of taking log entry wise for each of these entries. And then you're limited to only taking matrices which have non-negative entries, right? Because log is not defined for negative and so on. So it's like mathematically, it's an interesting question. You know how to take log of numbers, right? And that too of non-negative numbers. But if you want to take log of operators, it's like a whole different question. And what you do here in when you have a positive semi-definite operator, you actually spectrally decompose the operator like Samyak has written here. And you can be sure that since the operator is positive semi-definite, the eigenvalues lambda I are all non-negative, right? That is the definition of positive semi-definiteness. And once you take the logarithm, how do you define the logarithm? You just take the log of the eigenvalues and you keep the basis, like the eigenvectors, unchanged. This is like a mathematical subtlety. How do you define the log of an operator? Because it's an operator, right? You have to define it in a precise way in order to deal with it. And how we do it is, if you have a positive semi-definite operator, you can just spectrally decompose it, leave the eigenvectors invariant, and then just act the logarithm on the spectrum in the sense that the eigenvalues. And you can be sure that it will be a mathematically valid operation because all the eigenvalues are already non-negative. And then you can, when you take the trace to define the entropy, you're just basically just summing this up, and then this extra factor of rho gives this extra factor of pi, and then the thing that you get is like sum over I pi ln I. Yeah, that's all. I just wanted to point this out.
Thanks.
And if you go in infinite dimensions, this all becomes more messy because this decomposition is not really. Let me not get ahead of myself. Maybe we can talk about math of infinite dimensions in sometime later. Okay.
We should have a talk on that separately.
Yeah. Okay.
So yeah, thanks, Satvik. Yeah, so the one more point I want to make is the reason why mathematically we are restricted to positive semi-definite is because we want, this is how I think about it, we want the diagonals to represent probabilities. So they have to be positive elements. So that's why these lambda I will be positive because they represent the probability. But yeah, so, and that's why we want rho to be positive, positive operator at least, positive semi-definite. Okay, so any other doubts? Because now I'll be going to thermodynamics. And I think Anubhav or Dhruva. Okay, Dhruva.
Yeah, so we've talked about the blocks here a lot. So are there, it's a common thing that you can only define the block sphere only for the qubit state and you can't do it for further.
Actually, I told you, right? There are ways of actually extending this concept to d-dimensional finite universe spaces.
Oh, you can do that, is it?
So the thing is,
okay,
you see, I want you to notice 2-3 things. One is that these elements are unitaries also, in a sense.
Yes.
Okay, and they are something known as orthogonal unitary. Okay,
right.
Read up about them. And the thing is, there are ways of defining more. So there is a proof that orthogonal unitaries exist in d dimensions, in any arbitrary dimension. Okay, so that proof is there. There's a unitary basis, in a sense, for these operators. There's a unitary basis, actually. So using that, you can always have some, trace of U0, U1 here, U2 here, U3, and hence you can define R1, R2, R3, R4 like that.
Right.
And hence you can, interpret that as some, hypersphere and things like that.
Hypersphere and the states lying within that hypersphere. Then can we also do the same stuff that, all unitary evolutions are just...
unitary evolution rotation. Will always be
just rotation
about the whole system. They will not add any information.
Okay. Right. So basically you're saying that you can extend this to multiple systems.
Yeah, it's there.
Not multiple systems. What I meant was
not multiple systems, higher dimensions. Yeah.
Higher dimensions, right. And multiple systems, what about multiple systems?
So this is what we talked about, entanglement and stuff. So
right. No, I mean the block sphere representation for multiple.
So you think about 2 qubits as another Hilbert sphere of a single qubit. Hilbert space of another, say 4 state systems, something like
that. Right. Okay.
So yeah. Because the thing is, because every element, I think there's a doubt. Every element can be, say, I can call some I element that will make, say, the basis of I of the 2-qubit system. I can represent that as some 0. You see. So there'll be more number of states.
Yeah, it'll just be 0, 1, 2, 3, 4.
Yeah, something like that.
Just 0, 1.
Yeah.
1 to 3, sorry. Right.
Anything. I mean, you can work it out.
Yeah. Okay.
There's another doubt in the chat. You need rho to be Hermitian, right? Yeah, you need rho to be Hermitian. We could use SU and generators as basis. Cool. Yeah, you need rho to be Hermitian. I mean, sorry, I think I didn't mention that, but yeah, that's important. Rho is Hermitian. Anything else?
Samyak.
Yeah.
Can you like go back to the previous slide, the block sphere one? Yeah, this one. So you say that the entropy is 0 for pure state. So when you are on the surface, so are there any operations possible which take a mixed state to a pure state? Because in that case, you are basically decreasing the entropy of a system. And is that allowed?
Yeah, because in those systems, that will not be a unitary operation.
Yeah, you need a non-unitary operation for doing that.
Yes, so by reducing, if you're reducing the entropy of one system, you're increasing the entropy of another system, really. So for example, I'll give you a very basic example.
For closed systems, it's not possible. No?
Closed as in, so okay, there are multiple definitions now. So let me be very clear. So this is important for everyone. Isolated systems are systems which cannot exchange anything, any particles, energy, or anything with the environment. Okay, those are isolated systems. I will call closed systems which can exchange energy at least with the environment. Okay, so what we are talking about here when we talk about unitaries are isolated systems. Okay, so that's a very important distinction that will be important in the thermodynamics part. So yeah, you can ask it out now. For isolated systems, it's true.
For isolated systems, it's true, right?
Because then, I mean, the thing is, then what you have to do is, say you have an isolated system in this box. Okay, now you can increase the entropy for the part of it. You can say you decompose this into, say, some 2 other density matrices, for example. You see, for example, in Dhruva's case, we were talking about 2 qubits representing some one state. So I do the opposite here. I have one big thing. I decompose it into 2 states. I don't know if this is possible always, but yeah, if you can do something like this, then you can have operations between them, then not look at this. You don't look at this. You increase or decrease the entropy here. But if you want a complete evolution on an isolated system, this cannot have a change in entropy because the complete evolution will be given by unitary.
Hey, in case of entanglement, look, suppose initially the states are separable and pure, so the total entropy is 0. Then you entangle them with C0 and then write down
total entropy. Okay, go ahead.
Entropy of composite system is 0, right? Then you write down the subsystems state, which is reduced density matrix for rho A, rho B, and you find out that the entropy of both system has increased. So the total entropy has increased overall.
Yes, so that's because you have lost the information on the correlations. That's the point I want to make here. Because there are some correlations that actually have some information content. You see, the correlations themselves have an information content. That is something that you have lost.
Okay.
That's why the entropy of both systems has increased. Because once you know the correlations, you will know exactly what the combined system is. If you do not know the correlations, you do not know anything about the systems.
Okay.
Yeah. So that. Anything else? Then I'll be moving on to thermodynamics, and we'll be using this stuff later on in the third part. Okay. So let me go on to basics of thermodynamics. This part I'll try to move a bit quickly here because most of us may already know it, If you have any doubts, you can always ask. But some parts include a lot of statistical mechanics. And if I go too much into it, I will end up explaining most of statistical mechanics, which I don't have time for because there's a lot. So some things when you ask a question, I may answer like, you just take it for granted for now, and we can have a discussion later on that. But I hope everything is fine in this part also. But let's see. Okay, so I'm starting the thermodynamics part. So I start the thermodynamics with classical thermodynamic cycles. Okay, so we know the simplest case are like heat engines, where a system interacts with a hot bath. For example, I can think of this as a big reservoir with a lot of energy levels, and this can interact with the system. It can give heat to the system, using which the energy of the system increases, and then this can do some work, but it can't completely convert this energy into work. It has to dissipate some energy into another cold reservoir. Okay, and in doing this process, the system starts at some initial state and ends up at the same initial state. Now, for classical systems, the states are actually represented by its energy value or its pressure or the volume in thermodynamics at least, right? Because they're classical systems. Okay, so here, this is something that we'll be interested in, the refrigeration cycle, where you have a cold bath and you have a hot bath, and you are actually taking some energy from the cold bath and putting it in the hot bath, which makes this cold bath colder. So this is how the refrigerators work, by making cold things colder. So yeah, to do that, you need to do some work on the system so that it's able to take out energy and put it in the hot bath. Okay, you have to do some work. So any thermodynamic cycles, this is just to show you remind you of some concepts. They are represented by such diagrams where, for example, here is the pressure, volume, and A, B, C, D are the different states that the system takes during the evolution. Now, there are some assumptions here at least in the classical Carnot cycle. This is the most efficient cycle that you can get. And the assumption is that these processes from A to B, B to C are all quasi-static. That means the system is always at some, for some small time it's at equilibrium, then it moves, then again it's at equilibrium, then it moves. It's like that. So it's more of a way to model thermostatics with some process. So it gives you many different equilibrium states in a sense. So the thing is here, what is happening is this just describes this heat engine, where here you have isothermal process happening, where you take in the heat from the hot reservoir. B to C is adiabatic, where you do some work. Here it's this describes basically the heat going out of the system at isothermal process, and then A to D is just going back. The system resets to its initial state. So these systems, like these entropy, the temperature, volume, pressure, are basically the state variables. The evolution is described by the change of these state variables. And what is important here, and what will distinguish us these classical systems with quantum systems, is that classical systems have a high number of microstates. And these microstates actually describe, just to remind you, describe average quantities like temperature. Okay, temperature is an average quantity of the whole system. Okay. Yeah, so this is what I just described. Heat engines and refrigeration cycles use systems to interact between two thermal baths to take energy from one and put it into the other while doing some work. So these are the kind of cycles that you see in thermodynamics, usually in the classical case at least. Okay. And this is the important point that we'll be using. Any thermodynamic cycles start and end at the same system state. Okay, so let's go. The next thing is the second law of thermodynamics, very important. Obviously, this just to remind you, I'm just putting it here, the Kelvin statement and Clausius statement. I'm not even going to read it. Okay, so what is important to us is that the second law describes a state function Okay, a function that does not depend on the process that is happening, but on the state of the system, using something like heat that depends on the process. So the entropy, the thermodynamic entropy, I label that by TH here. The thermodynamic entropy is a state function which is described as the integral over this change in heat by the constant temperature. Okay, so this is the reversible, in a reversible process that is quasi-static, this is the amount of heat that is taken in or given out. So that leads to the change in definition of thermodynamic entropy. Okay, and for isolated systems, the thermodynamic entropy always is greater than or equal to 0. Okay, so this is something that is also important. Okay, so this is basically the second law. Okay, so now I'll talk about thermal equilibrium and free energy. So this is very important, but the thing is there's a lot of literature on this. So this is the part that I'm not going to explain fully. Some things here you can take it for granted, but yeah, I hope it makes sense. I hope it's cohesive. Okay, so what we're talking about here, what we'll be talking about throughout actually will be a system that is coupled to a large reservoir. Okay, so there is heat, there's some energy exchange that can happen between the system and this large reservoir. And the system it has microstates of energy En plus 1, En minus 1, and you can have some occupation probabilities, Pn plus 1, Pn minus 1 on each of these. Okay, this is just for the system. Okay, now I say that microstates of isolated systems in equilibrium are all equally probable. So this is an assumption taken in statistical mechanics. The point of this being, as I said, so you remember the completely mixed state had equal probabilities of occupation of the basis states, right? That means we do not have any information about those states, about that state. This kind of describes the same thing because we do not really have access to microstates, so we do not know anything about the microstates. That's why each microstate is equally probable. So if there are some n microstates, I have the probability of occupation of one of the microstates will be 1 by n, and that's it. It's as simple as that. But this is true for isolated systems. So here what we have is, we have multiple energy levels for the system, but it's interacting with the path. So this has also a large number of states of itself. Okay, what this leads to is the system, when it's connected to this thermal reservoir as shown, the probability of the occupation of nth energy level at equilibrium, okay, is the Boltzmann distribution that is given by this. So probability of occupation of the nth level is given by e power minus En by kBt. Okay, and here is the summation over all i's, all the microstates. Okay, this is known as the partition function Z. Okay, and 1 by kBt is the beta, is known as the inverse temperature beta. Okay, and kb is the Boltzmann constant. And yeah, so this is the occupation probability that comes from a lot of statistical mechanics. It's not very hard to prove, it's just lengthy. Okay, so this is the occupation probability of the system state to be in one of these energy states. That's all. Okay, of the system to be in one of the energy states. This is the probability. Okay, so now there's a very important result that is, I don't think it's elaborated a lot, but I thought it was important to show that this thermodynamic entropy is related to the Shannon entropy that we talked about. Shannon is this minus pi ln pi. So right now we are still in classical, so we won't talk about density matrices, but the classical states, okay, which have some probabilities associated with it. So this is actually an equivalence that is shown that is true always. Okay, so the proof goes like this. Okay, this is an exact equivalence. So when you have this, so let's say this is true, okay, for now. So you differentiate this entropy with respect to the probabilities actually. So I've written n here, doesn't matter. Okay, so what you get is this dpn ln pn, because summation over all n dpn is equal to 0, because you won't be able to change the probability. Let me just write that down. The summation over n dpn is equal to 0. So the complete change in probability is obviously 0 because summation over n Pn is equal to 1 always, right? So this is always 0. So using that, we get this. Now, this ln Pn from here, from the Boltzmann distribution, can be written like this: minus En by kBt minus ln z. Okay. Now, what this gives you is that, again, we use this here along with this to get 0. We are left with just dPn times the En by t. Okay, the kb also disappears. Now this I can again use differentiations to expand as d of En Pn is equal to this plus that. Okay, so this is what we get, and this term actually is the reversible work. Oh, sorry, the change in energy. Sorry, this is the change in energy, and this is the average change in the work done. E minus W. 1 second. Yeah. So this can be written as the change in the average energy minus the change in the reversible work done. Okay. So divided by T, that will give you the reversible heat that you have for reversible process basically. Okay. So hence you see I showed this equality that minus Kb summation over this dPn ln n is equal to this change. So that's why this equality holds. Okay, and I'll just be using it, and I will be going to a quantum version of it. Okay, so this is something I just wanted to show. Not very important to remember, or there's nothing much to understand really, but yeah. This to go from here to here, we say that the process is really slow and the coupling is really small. So that's what we have used here, but that's okay. All right then, I hope you understood this proof to show that the thermodynamic entropy and the Shannon entropy are equivalent, and the constant is given by the Boltzmann constant. Okay, now we come to an important concept that is true whenever this system is coupled to a large bath at a particular temperature T. Okay, so there is something known as the free energy. Just to remind you, this is a thermodynamic potential, okay, and that is equal to the average energy of the system minus T times the thermodynamic entropy. Now I can write this thermodynamic entropy as Kb times the Shannon entropy. So that becomes S becomes beta times F minus this E. Okay, so this is the free energy of the system. Now what does this describe? In the above scenario, thermal equilibrium is a state of minimum free energy. So whenever you want to define equilibrium, another way of doing it is maximizing entropy. Okay, and that leads to the fact that you minimize the free energy of the system. Okay, free energy in a sense is the amount of energy that the system has to do some work. So any work extracted from the system is bounded by this change in free energy that you get from any process. So decrease in free energy for the process at constant temperature. So whenever you define free energy, we define it at a constant temperature. Okay, so any process that is changing the free energy, the work done during that process will be bounded by this free energy. Okay, this is the highest value that you can get. So, just one more point to be made here. When you talk about this work, now think about this. The equilibrium state has minimum free energy. So to extract maximum work from a system, what you have to do is you have to take it to a state of minimum free energy, that is the equilibrium state. So if you have a system, you attach it to a bath and then leave it, it'll go to equilibrium, and hence, or any process actually that just brings the system to the equilibrium state does maximum work, can do maximum work in a sense. Okay, because you have maximum change of free energy then, right? I hope that makes sense. Okay, so free energy really tells you about the maximum work that you can do, okay, that a system can do during the process. Now we quantize the whole picture. We put quantum mechanics in this whole picture using the Boltzmann distribution. So first thing that I need to tell you is the Hamiltonian will be described like this. For example, initially for qubits, we described it as delta 1, 1. This just describes the energy of the system. Now this Boltzmann distribution is given by this. I can write that as, again, so this e power minus beta h. Now Satvik already explained to us how functions act on operators, right? So you just take the eigenvalues and you put it up here and you put the state vectors down, right? So you see this is a matrix and I'm taking the nth element of that. I am saying that that matrice's nth element is this probability, right? So this matrix with the diagonals being the Boltzmann distribution is known as the Gibbs distribution. Okay, so here this trace of e power minus beta h will give you the partition function, and this is the Gibbs distribution. Okay, just two more points. I think the free energy of such a distribution now will be given by the Shannon entropy and the average energy calculated using the Hamiltonian. Okay, of any state, any quantum state, f of rho. And the Shannon entropy becomes the von Neumann entropy. I'm sorry, I said Shannon before, but this becomes the von Neumann entropy, and this is just the average energy of the system. So this is the free energy that is calculated in quantum systems, basically. Okay, and just to show you, the Gibbs state still has the same free energy as an equilibrium distribution, that is -1 by beta ln z beta. Okay, so we are done with the thermodynamics part. Any questions?
So is this Gibbs distribution an operator here?
Yes, it's a density matrix. So
okay.
So if you want to write it, I've actually written it later. If you want to write it for a qubit case with Hamiltonian, say the Hamiltonian is delta 1, 1, right? So the Gibbs distribution will be written as something like 1 by z. I'll just put it outside. This is like the normalization. I'll put a 1 here. I'll put an e power minus beta delta, because delta is the energy. So I made the energy of the zero state 0, right? So that's why you have a 1 here. E power minus beta 0 is 1, and e power minus beta delta. So 1 by z times this.
Right. To basically take the exponential of the entries of the matrix.
Yes. Okay. Any other doubt? I hope people understood and they don't have doubts because they understood stuff, not because I was too fast or something. Because you can ask doubts whenever. Okay.
So with the construction that you had given at t going to 0 limit, you will be in a pure state. The Gibbs distribution, which you had just written out. T goes to 0 limit would give you a pure.
Yeah.
Okay.
Yeah. True. Because you see, I mean, the thing is, when you go to 0 temperature, you go to a ground state. Your state doesn't have any energy. So that's the insight, kind of.
Okay. Thanks.
Yeah. Anything else? Okay, I think I'll go on then. Okay, anybody want a break now? It's 5:30. Shashwat, what do you say? This is the third part now. Or do I continue? You can say, whoever. Do we take a break now or do we continue? What do you guys want? You can write in the chat also if you want.
Yeah.
Can it be like last week where the next half happens tomorrow?
Okay, we can do that, sure. I don't mind. But yeah.
Were you planning to keep this part 3 in your next part, or there was something else?
No, this part 3 was actually for today. I underestimated kind of the content.
How long is this? Like,
this is
time lagega.
Why don't we continue?
Other
How much?
concepts,
How long will it take? Half an hour?
It depends on the doubts, but should take half an hour, yeah. Half an hour to 45 minutes, actually, I would say. We can, I mean, it depends on you. If you want to do it tomorrow, we can do it tomorrow. If you want to do it, if you have time now, we can do it now, because yeah, we can take like a 2-minute break, and if you want to go on to this.
Yeah, it's fine. I think we can go on till 6 at least. So it's fine.
Okay, so do we take a break now? I mean,
yeah.
2
minutes break.
Cool.
2 minutes break.
It's only 5:30.
Anand, recording. Pause.
Okay, now we'll talk about the work that I did during my master's thesis, like one part of it, and that's something known as indefinite causal orders. Again, we'll be restricting ourselves to only qubits. Okay, so to understand indefinite causal orders, first we'll understand what causal orders are, and then we'll understand how we create and what is really indefinite about indefinite causal orders. Then we'll see some applications of it, some advantages of it, and then we'll look at some thermodynamics of this indefinite causal orders. That's the last part. So yeah. So to actually define what a causal order is, I want you to think about an experiment. Okay, let's say again, we have Alice and Bob, okay, as usual, and they are inside laboratories. Okay, these laboratories are closed, as in there is no information exchange between Alice's laboratory and Bob's laboratory. Okay, but the only thing that they can do is to exchange information is that if I give them a box, okay, this box can contain any system, okay, any system of your choice, and Alice can do something on this system. Okay, after doing something on the system, she just goes and gives it to Bob's lab. So this system it gets changed by Alice, goes to Bob. Bob can also do anything he wants on the system. Okay, and then it goes. So you see the time is upwards here, so pay attention to that. So now Alice can encode some information on the system. For example, a result of her coin toss or something like that. She can just do anything to it and then give it to Bob. Now Bob can use that information that Alice gave to do something on the system, to selectively do something on the system, right? So this means that Alice, in a sense, can signal to Bob by sending some information, which Bob can use. Alice has the ability of signaling to Bob. Okay, but because time goes upwards and Alice gets the box first, Bob can't signal to Alice. Okay, because there is only one box being exchanged and the labs are closed, so there's no other kind of exchange that is possible. So because Alice can communicate to Bob in this direction, the operations of Alice are known to be in the causal past of operations of Bob. Okay, any operation. Now, bidirectional signaling is forbidden, right? There are no causal loops because time flows only upwards and we have only one box. And A and B, essentially, because Alice can do whatever she wants, Bob can do whatever he wants on the box, on the quantum system, say, we represent the actions by CPTP maps, by the phi map that I showed previously, by the channels, essentially. So you have a state rho, it goes through channel A or Alice's channel, then goes to B, that is Bob's channel. So that means Alice is in the causal past of Bob. And in the other scenario, where Bob's laboratory first gets the box, then rho can go to B first, then A, then come out. That means Bob's actions or Bob's operations are in the causal past of Alice's. Okay, and so we are only talking about qubits. So all input, output, Hilbert spaces and stuff, this is just something I wrote long back, are the same. So that's true. Okay, so there we go. Now, to describe what indefinite causal orders are. So the causal orders are simple, right? A before B or B before A. The A and B are just channels, right? To define what indefinite causal orders are, I'll need some ingredients. And these ingredients I'll use to make a interferometric setup, okay, like a tabletop optical setup. And then I'll show you what is indefinite causal orders there. So the main ingredients that will be required to make this setup is known as the quantum switch. The ingredients are there are two quantum systems that we need. Okay, two qubits you can think of as internal degrees of freedom of a single photon. Now, this single photon, you can have the spatio-temporal modes as the target system. This is the target system on which the operations act. For example, the channels A and B of Alice and Bob, they act on this system. We need another degree of freedom known as the polarization, right? That we'll call the control system. That'll be in another Hilbert space HC. So this is rho S in Hilbert space HS and rho C in Hilbert space HC. Now this photon, single photon, is given by the tensor product of polarization and the spatial modes, obviously. So it's like the cat plus the grin gives the complete cat. Cat's body plus the complete cat. So it's like that. Okay, you can't describe a photon without any of these. Okay, so now we can, the point is that we can act on these spatio-temporal modes without affecting the polarization. We can do that. That's possible using certain maps. Okay, using certain instruments, we can do that. And we can use the polarization to do some cool stuff so that we can create the indefinite causal orders. So we'll see how that is done. So yeah, this is very important point that the channels only act on these spatio-temporal or the target system modes. Okay. So the complete state rho of the system, rho of the photon is given by rho S, that is the target system, tensor, rho C, that is the control system, right? Okay, so moving on. Now I'll show you the setup. Yeah, so this is the quantum switch. Okay, A and B are the channels described by the Krauss operators that I was talking about previously. And A has a set of Krauss operators for Alice, B has a set of Krauss operators for Bob. Now, what happens? So first, let's just look at this side diagram here. So these are known as polarization-based beam splitters or polarizing beam splitters, okay, PBS. So these are special kind of beam splitters that act depending on the state of the polarization of the photon that is passing through it. So for example, if the state of the polarization is horizontal, so again, polarization now is a qubit degree of freedom, okay? And its basis states can be represented as horizontal and vertical, okay, given by H and V. Instead of 0, 1, I'm just calling it H and V, okay? So horizontal by H, vertical by V. If horizontal passes through the polarizing beam splitter, it will just go through straight. If the vertical one tries to go through the polarizing beam splitter, it'll get reflected. Okay, it's as simple as that. Okay, and this gives you the state of the target system. Okay, L. L is just the direction in which it's moving, but that's okay. L and R. So let's see. We have our polarization. We have our target system. Let's see what happens. Okay, just follow the arrows here. So first, because this is horizontal, it will go through the polarizing beam splitter. So first, this photon will be acted on by B, the channel B. So this psi state will get acted on by B and turn to some other state. Okay. Now again, because the polarization does not change, it again goes through the beam splitter. And you see, these are just mirrors and they just get reflected like this. It goes through, just keep following the arrows, goes through again. After that, the A is acted on. The A acts on the side, okay, on this state, on some state that comes from B. So the final thing that you get is H tensor, B acting on the state psi, and then A acting on this complete state. Okay, it's just a composition, like B acts first, then E acts when the polarization remains horizontal. So this is the state that you get. Okay, now what I do is after it comes out, I just do the measurement on the polarization. So this is just a measurement on the polarization. I measured this state. So you remember, like the quantum meter that we have, we measured only the quantum meter. So here I measure only the polarization. without affecting, without doing anything to the system. Okay. So when I measure horizontal, I know that B happened. B happened before A, right? B was in the causal past of A, right? And yeah, so now let's go to the other one. So let's start with V. Okay, if you have V here, then what happens? Then let me just erase this part, right? Now, when V happens, it first gets refracted, because I told you every time we have a vertical polarization, the polarizing beam splitter reflects. So it reflects, goes to A acts on psi, reflects again, reflects, goes here, reflects, again reflects. So you see it reflects here, goes to B acts on it now, goes here, and then again reflects. So here A happened before B. That means the final state is something like V tensor, the B happening before A acting on psi. Okay. So this is what happens. So A acts on psi before B. Okay. So the thing is, without looking at the system, if I just measure the polarization as V, I know that A happened before B by just measuring the control, the polarization. Okay. So you see, if I write a density matrix for the control, rho C, with some P0 and P1 and 0, 0 on the off diagonals, this will just tell me that the probability of, so this is the horizontal part, HH, and this is VV, okay, VV. So this part will tell me that B happens before A with probability P0, and this part tells me that A happens before B with probability B1, P1, okay, or 1 minus P0. So you see the diagonal elements talk about definite causal orders, A happening before B or B happening before A. Okay, the incoherent terms, definite is related to the definite causal orders. Okay, now I superpose the polarization in a plus state, H plus V by root 2. Okay, here it's like both orders happen simultaneously, right? Because this is in a superposition. So both paths are taken in a superposition. So now, so the thing is, I've not written it here, but this is the plus state, okay? And the minus state is given by H minus V by root 2. Okay, so the thing is, when you measure now, so when the control is measured in this plus minus basis, when you start the control in the plus state, you get access to the off diagonal terms. You get access to some terms here, because you see in the HV basis, this is no longer 0. This has some C. Okay. This is some C, this is some C star, and this has some P, and this is 1 minus P, right? For this is rho C. So you see, these terms are correlate with the path of the system, and hence the causal orders of the operations of the channel on the system. So when you measure plus state, when you do the control measurement and measure the plus state, and say the plus state comes out, right? Now this plus state for the control does not correspond to A happening before B on the system. It does not correspond to B happening before A on the system, but it corresponds to something that is indefinite. So this is the indefinite causal order that I was talking about of channel actions. Okay. So yeah, so this is what happens. Now to really look at what happens on the system when you prepare and measure in the plus state, let's see what happens really. So to do that, I'll give you an example. Okay. This example involves the channels being something known as entanglement breaking channels. Okay. So entanglement breaking channels are given by this map, where this is the poly X matrix, this is the poly Y matrix that acts on the system, and this is the map. So you see, this is called entanglement breaking because what you have is really a diagonal state in the plus minus basis. So any quantum information is erased. Because any quantum information is erased, and for entanglement, you need some superposition. If you had any entanglement initially, that is non-existent now after this channel has acted. Okay, so this, in a sense, also reduces the information of the system, at least the quantum information, in a sense, because it really removes the coherence terms. Okay, now let's say we put two of these entanglement breaking channels inside the quantum switch, start the control in the plus state, and we have a rho s. Okay, what you see finally is that when you measure the plus state for the control, your final system state will become rho s, the same as initial state. Okay, and if you measure minus, you will just get a poly z acting on this rho s, and hence you can get back rho s by just doing a u dagger here, or z dagger. Z dagger is equal to z, so just have act as z or poly z on the final state after measuring minus to get back your initial state. Okay, that means any entanglement that was present in the initial state is retained here. By using two entanglement breaking channels in the switch, all I've done is I've measured the control and I have preserved the entanglement. But the passage of the information has happened through two entanglement breaking channels. And if any linear combination, any combination like this, it can be shown, any combination like this cannot ever, give you any entanglement in the final state. So this is something that is interesting from information theoretic point of view for communication. If you want to create a channel where you only have entanglement breaking channels, you can actually retain all your information by using it in a quantum switch. Okay, so the channel can't, but to be in the quantum switch can. So this is an information theoretic advantage that you get. Okay, so what is happening, right? In summary, let's say we had a channel N1 and then N2. So the measurement of the HH basis gives you N1 before N2. Measurement of V gives you N2 before N1. And plus state gives you the superposition of the two causal orders. And hence indefinite causal orders when you measure the control in the plus minus basis. Okay. Now, the quantum switch itself, as you can see, it is also a quantum channel, right? And hence it has Krauss operators. Okay, this Krauss operator. So this quantum channel is before the measurement of the control. So if I don't do this measurement, the state that I get here describes the quantum switch final state. After the quantum switch channel has acted on the initial state. So the quantum switch has two inputs: the control and the system, the target system. Hence, the Krauss operator quantum switch is given by something like this. When HH is acting, that means 1 happens before 2. So you see the Krauss operator of channel 1 happens before the Krauss operator of channel 2. And when VV is the polarization, then Krauss operator of channel 2 happens before the Krauss operator of channel 1. So the quantum switch essentially is giving you a channel with such Wij as Krauss operators. By Wij, because you have two qubits here, the control and the system. So yeah, and these Krauss operators are in general non-commuting, because if they commuted, there would be nothing to distinguish between the operations themselves, and hence you can't talk about causal orders. We need distinct operations to be able to talk about causal orders. Okay. Is everything clear till now? Any doubts here? Because now I'll be going to thermodynamics. So,
hey, what is your D here? I mean,
the V.
So the entanglement breaking channel.
Oh, D. Okay.
Yeah.
This
So
is
how do you construct it physically?
So I'm not sure, but you can always, this is a map. So you can always, so you see these X, poly X and poly Y are cross operators. By two, right? By root.
It's breaking entangle between special mode and the internal degree of freedom.
No, sorry. Okay. The thing is, this rho S, so okay, let me just write it down. Rho S could be a qubit, right? P 1 minus P, C star, right? So now the thing is, this presence of this off-tidal parts can tell you that there is some entanglement present, right? If there is entanglement present, this is definitely there.
But it is single particle system right now. If you write the
no. I'm not telling you anything about this. I mean, when I write it as a qubit, yes, but really, this could be entangled with some other system also, which I'm not seeing here, which I don't know.
Okay.
So this could be entangled with something else. That's what I'm saying. And presence of these coherence terms tells you that these can be present. But if you remove these, you don't have that.
Like right now, from your expression, it looks like you are making it just like mix, right? You should beginning with the pure and you just mixing it. So somehow you are measuring.
No. So the initial state of rho S. So okay, here's the thing. So this 0, 0 could also mean something like a 0, 0 state. Okay, so I have hidden all these facts, but yeah. So could also mean something like that.
Okay.
So you can actually describe this rho S as constituting of two other quantum states.
Okay.
Where this actually becomes blocks.
Can I chime in quickly?
Yeah.
So point about entanglement breaking maps is here we can think of it as the channel. The action of a channel is described for a single party or a single subsystem, right? So this is the act. This is how the channel is defined, and here there's no talk about a second system, right? But the definition or the concept behind entanglement breaking maps is, if let's say we talk about a bipartite system, any bipartite system, let's say separable or entangled, no matter what the state is, if you act this map partially on one of the systems and leave the other one as it is, so the action would be like D time tensor the identity channel on the second system, then you would be guaranteed, no matter what the other system is, the outcome would be separable. So that is why they are called entanglement breaking. The action, the channel is itself defined for a single party, but it is such that no matter how you associate
that's clear to me. But what I'm confused with is that in general it is defined for bipartite or multipartite, right? It's more than one party. And if you are like this operation looks similar to single particle measurement. Like if you try to perform any measurement on a single particle, it will mix the system, right? If it is not in the same base.
Yeah. So that is another. Yeah, this is like another. So this is like what is called quantum to classical channel, if I'm not mistaken. So basically, in action of a measurement, you perform a measurement on a single party, and then depending on what the outcome is, you replace it with a definite thing. So this is the action of this is the single party channel. But the point is, if you apply this channel on a bipartite system only on a single party, then you can be sure that the combined state after the partial application of this channel on only one system, the combined state would be separable no matter what you started with.
That's good. Okay.
Yeah.
There is one other question, but I will ask at the end. Okay.
Let me just be clear here. This rho S really just talks about a single qubit system, for example. These are poly X. This could be entangled. You don't know. Okay.
Okay, it's path entangled anyway, but
yeah. So okay, I will proceed. Yeah, so I told you about the cross operators of the quantum switch now, because quantum switch itself is a channel. Okay. And yeah, so now to talk about the thermodynamics, we'll be putting some thermalization channels inside. Okay. Now, I told you previously that any thermalization operation basically gives you a Gibbs state for quantum states. So there are two equivalent ways of describing this. One is just through a CPTP map. So I call this a thermalization pin map, so which takes any state rho s, any state, any qubit state, and gives you the Gibbs state given by this. Okay. And there's another equivalent way of thinking about it, is that thermalization as swap gate. So what it does is, say this, so this is the swap gate, and this is a total unitary operation again on this two-party system. Rho s is swapped with the second system, which is the Gibbs state. So you see, when you're just looking at the system, it is just like the thermalization pin map. Rho s goes to the zeta beta on the Gibbs state, right? But here we can also look at the bath state. We can model the bath as a single qubit which interacts, and that becomes rho s. So you see, any energy change that is happening here is opposite to the energy change that is happening here. So in a sense, we can talk about, you know, energy going from the system to the bath, or the bath to the system. You can talk about things like that when we model it like this, and we will do that shortly. So yeah, so for this state, again, I told you the system Hamiltonian is just delta 1, 1. The thing is, when we talk about the quantum switch, we have two parties, the control and the system. We are not really looking at the energetics of the control. So the control is assigned as 0 Hamiltonian. Okay. So that is an important point. So only the system is assigned a Hamiltonian of delta 1, 1. Okay. So now we have a Gibbs state, which is supposed to be at equilibrium, which with two other baths. The baths are present with Alice and Bob in their laboratories, and all have temperature beta or T, whatever you want to call it. Okay. And because they're all at the same temperature, any definite order, for example, this before this, or Alice before Bob, will not really do anything to the system because it's already at equilibrium. So the energy cannot increase or decrease because there is no more exchange happening, right? Because all this is doing is, if you think about it mathematically also, all this is doing is it's giving you a state zeta beta, which is already there. And this is also doing the same thing. Okay. But if you do not look at the definite causal orders, but the indefinite causal order, which is created by starting the polarization in the plus state. Okay. And when you pass it through this quantum switch, what you'll get is, upon the measurement of the plus state, you see that the system temperature is colder than the initial one, because the system state really changes to such a state. And when you calculate the temperature of this state by writing it in a diagonal form, you'll see that the temperature is lower than beta. All it has done is it has gone through these channels and come out, and the control has been measured. That's all. For the minus measurement, you will get that the system temperature is hotter than initial. That means the temperature has increased from this beta, and the system is at a higher energy, can have a higher energy levels now, you see. So indefinite causal orders is somehow giving you energy into the system using just thermalization with the same temperature. All three things are at the same temperature, but you're still getting an increase or a decrease of temperature depending on the measurement result. So this is something weird. In papers such as this one, people say, they have said that the heat or the energy increase here, for example, if you measure the minus state, the heat comes out from these thermal reservoirs and goes into the system, hence increasing the temperature. And in the plus measurement, the heat actually comes out of the system and goes into these thermal reservoirs during the operation of the quantum switch. We'll be analyzing this claim essentially. We want to know where is this energy coming from. Okay, but first let me tell you about a refrigeration cycle that this paper has used to really show you the advantage, the thermodynamic advantage. Okay, so imagine, so again, a thermodynamic cycle is something that starts at a certain system state and comes back to the same system state, right? So you start the system at a temperature Tc. Okay, so all the 3 baths that we took here are at temperature Tc, say. Okay, and I have another bath somewhere else at temperature Th. Th is greater than Tc. Okay, and this actually means that beta H is lower than beta C. Just telling you because inverse temperature. Okay, so I start my system and the 2 baths inside the quantum switch at temperature Tc. Now I make a measurement on the control after passing the system through the switch. I make a measurement of plus, say. If plus is measured, that means according to the paper, heat has come out of the system and gone into the reservoirs, hence making the system colder than initial, right? Now to get back the initial state, all I have to do is classically thermalize with the 2 baths so that whatever heat I put into the system, I can get back, put into the reservoirs, I can get back into the system. So this just is a cycle when you measure a plus. So you start here. So you keep measuring till you get a minus state. Okay, once you measure a minus state, what you do is your system temperature becomes, say, something like T prime S. Okay, so this T prime S is higher than, 1 second, just make it here. T prime S is higher than TH. So now what you can do is you can classically thermalize with this hot reservoir that we have, another hot reservoir. So what is happening? You have taken out some energy from the cold reservoirs inside the quantum switch and put it into the hot reservoir. Okay, and then you classically thermalize back to the system state. So you see, this minus this energy has come out of the cold reservoir and gone into the hot reservoir. I hope this is making sense. So in a sense, this is like a refrigeration cycle, right? We have created a refrigeration cycle using our quantum system as the working substance, the system that acts between the reservoirs in the refrigeration cycle, right? So, and this actually depends on the measurement results. So what they have said is that without really having any, energy, what do you call it? Doing just measurement, doing just a simple measurement, you are actually taking out heat from a cold reservoir, putting it into the hot reservoir, and we have not really done any work here, essentially, right? So that's what the claim of the paper is. We wanted to analyze essentially where the energy is coming from. The claim was the energy is coming from the reservoirs, but we did not agree with that claim. Okay, so what I did was, for different temperatures, so this x-axis is the cold reservoir temperature decreasing. So the Tc, I decrease this towards the right, and this is the final temperature that I've plotted. Okay, so as you can see, these are different plots, and I have measured the control, the polarization degree of freedom in different directions, not just plus minus, between h and v, any angle between h and v, cos theta by 2, sin theta by 2. Okay, so this can be represented on the block sphere also, if you can see. So for example, the theta equal to pi by 2 gives the minus measurement of the control. Okay, so this is the indefinite causal order part. Theta equal to pi, 180 degrees, gives you the temperature of the hot reservoir. That is the indefinite causal order part. Now you can get something like a population inversion. That means a negative temperature for certain values of the reservoir temperature for theta equal to 135 degrees. As you can see, this line is going below 0. So you're getting really negative system temperature here. So this is something interesting, because this plot is essentially telling you that the measurement is, in a sense, affects the amount of energy that comes into the system. Okay, now we want to analyze where is the energy coming from, right? So this is just another plot. This is not very important. Yeah. So to analyze where the energy is coming from, we analyze the claim. The claim was the energy is coming from the reservoir. So we model the reservoir as these thermal bits, thermal qubits, and this is just my schematic representation of that whole interferometer. Right. Now I told you that the pin map, the thermalization pin map, can be actually modeled by swap gates with the thermal state. So these states, these thermal states, are actually talking about my thermal reservoirs. What they say is that after the measurement of the control, for the plus state, what I should get for the plus measurement of the control, what I should get is increase in the temperature of the system. System temperature should increase. That means my thermal reservoir temperature should decrease, right? Because energy is coming out of here and going into this. Oh, sorry, that was, I think I said the opposite here. So this is for the -1. Okay, but you get the point. So here, through this, we have access to the states of the thermal reservoirs in a sense. Okay, so for this, we can actually write a whole unitary. Like this is using the unitaries, we can write the cross operator of the quantum switch. Okay, and what we see is that the final reduced states for the system and the baths after the measurement of the control are, the system is in this state. This is what we saw already. It's either plus or minus depending on the plus minus measurement. But when I saw the first reservoir, it was at the same state. When I saw the second reservoir, that was also at the same state. Okay, that means when you measure the control in the minus state, all temperatures of the thermal reservoir, the system, they all increase. Okay, and if I measure the plus for the control, the temperature of the thermal reservoirs and the system, they all decrease together. Okay, so it does not look like any energy is coming from the system, from thermal reservoirs and going into the system. So you see, so where is this energy really coming from if it's not coming from the thermal reservoirs? So the thing is, this measurement process, as I told you, has ancillary, right? We have a quantum meter there. So that quantum meter is not modeled here till now. So when you use that quantum meter, you can show that any increase in energy or decrease in energy is coming from that measurement process that occurs. Okay. So I think that's all I want to talk about. So here, one more thing I did is that, you see, finally, when you talk about this state before the measurement of the control, what you'll get is a four-party entangled state in a sense, or correlated state here. Because you have the thermal reservoir, you have the control, you have the system, you have another thermal reservoir, right? So this is a big state. So the thing is, people say, okay, because it is a thermal reservoir, decorrelation should happen with the bath quickly. And hence this entanglement between the baths should not be present. So I decorrelated it here before the measurement of the control. Still, there was no change in results. So it really looked like any increase or decrease of energy of the system is coming because of the measurement process itself. Okay, so this do not look at this. This is, I had to remove it. I cannot remove it. So yeah. Okay, so I think that's all for today's talk. Yeah. So this is just summary. It looks like the energy is coming from the measurement of the control only. So that's what we saw. So when I talk about activation of free energy, I talk about that temperature increase or decrease, because free energy is 0 or minimum for the thermal state at a particular temperature. But when you increase the temperature, you can have some kind of an activation of free energy. So that's what people claim. By using the quantum switch, there can be an activation of free energy. But this activation comes only because of the measurement of the control. So there's a more rigorous way of proving this, which I'm not going into. It'll take a long time, but it's already 6:15. So I want to end it here. Yeah. So thank you. These are the references. Yeah, thank you. So these are the guys who helped me a lot. So yeah, thank you. Any doubts?
Did you guys hear the clap?
Oh, there are chat. There.
Anubhav would be there.
Why is he speaking in the chat?
No. I don't. There is no chat. There is no chat. Sorry.
Oh, okay.
Yeah.
Questions?